Let's just zoom in. Today's session will focus on generating these plots that we have in the book in R. Now, when I say these plots, think of it as three different levels. There's the level of the raw data, which we shall create using a relationship such as this red one. There's the level of fitting a linear model to the data. And the third level is extending everything we've done on this left chart to 10 or however many different data sets, which shall each give us a different linear fit. Let's move to R. Might even increase my font size slightly. So that would be under, not appearance. Yeah, it is appearance. So let's do it font 18. So that's this over here. And we need to generate, and we can include it as a comment, generate 100 observations, 100 x comma y observations. This is simple linear regression where we're taking a single input variable. Generate 100 x comma y observations, and this is synthetic data. So generate 100 x comma y observations using some predetermined linear relationship y is equal to beta naught, I'll just write it as a and b, a plus bx, and some predetermined linear relationship and a zero mean random variable as the error term, epsilon. The linear relationship as the true relationship f. Relationship, this is f. Okay. So this is the first layer, right? This is the first layer. This is the first layer of how we're going to think of this material. So layer one, creating a raw data set. That's layer one. Layer two is fitting. Layer two is regressing y on x using simple linear regression. So this means minimizing the residual sum of squares. That's layer two. Layer three is repeating previous two layers using multiple data sets. Okay. So repeating previous two layers using multiple data sets. Now, let's start with layer one. And we need some kind of relationship. So we'll define A, and I'll do it just like what the book is taking. The book has a y-intercept of 2 and a slope of 3. So A is 2 and B is 3. If you like, I could write them as mx plus c, same thing. So this is your c and this is your m. Okay. Now, we also need the error term. Now, the error term has a mean of 0. So we'll call it, should I write mu as, maybe not mu. Why don't we type instead epsilon mean of 0. Epsilon is the error term, and epsilon standard deviation. Standard deviation is just the square root of the variance. And as we keep on reminding each other in these sessions, it's not a random variable if the standard error or the variance, same thing really, is 0. So we need a positive. It's never negative. It's always a positive measurement, or 0, I guess, strictly speaking. But if it's 0, then there is no randomness. You have 100% certainty. Imagine it's your coin toss, and each time you know you're going to get heads. You get heads, you get heads. There's no variability over there. Let's take a random error. Let's take a standard deviation of maybe 20, and we'll see if we can change that if necessary. Okay. Now, they're using from -2. So their observations are from -2 to 2. Not necessarily, the input isn't necessarily, some observations have the same input. Some observations have the same input. So what we could do is, to generate the x's, we could say, let's take a uniform distribution, generate 100 between -2 and 2. And you can see it over here. These are our x, the x component of our observations. Okay. Now, how do you create y? This is synthetic data. We're generating it ourselves. We're not going out and interviewing people or taking measurements. Each y is going to be a function of x. So I say a plus b times x, and that's without the error term. So like this, like this, like this, like this, like this, and like this. I can now plot the data. I can now create a scatter plot. Plot x comma y. And what we should expect is that each observation, all observations lie on the same line. And that's exactly what we have over here. Now let's introduce the error term. And I'll create an error term for each variable, for each observation, epsilon. It's independent of x. That's one of the major assumptions. Epsilon is, let's take a normal distribution. Let's take a normal distribution. 100 of them, 1 for each observation. The mean is epsilon mean. The mean is just 0. Epsilon mean. And the standard deviation is just epsilon standard deviation. And now, instead of y being defined as a plus b times x, we will add this. You may wish to keep slightly more legible this way, isn't it? Plus epsilon. Epsilon. So let's do it. Epsilon y. And that didn't work. I must have a typo, right? So this is epsilon. Now we have this. And if I plot, now this is our random data. Now, I would say we've taken such a large standard deviation. Large means nothing on its own. But when you compare it to the intercept and the slope, that's what we mean by large. It's relatively large. That if you had to look at this data in a practical situation, if you had to collect that data, there would appear to be no relationship between y and x, or just a very marginal relationship. Well, let's see. Let's see. We're now going to regress. We're now going to regress. And how do we regress in R? You don't define each formula, although it might be a really good idea to actually do this from first principles. But there's actually a function called lm. lm, the formula is y is going to regress on x. The data, we don't have data, do we? I think it needs a data frame from us. So do I know how to do this, or will I have to do it in Excel? Data frame. I'm amazed that worked. So let's save it as data 1. This is our first data set. And now we have data 1. We have a slope of, so we have 0.2033. That's the intercept. And I guess this is the x coefficient. So this would be the gradient. It is the coefficient of x, not the value of x, the coefficient of x. It's actually 3.24. Can we reduce this? Yeah, probably. If you take a larger standard deviation, if the error term is larger, and let's do that right now. The data is kind of more dispersed, and it's a lower slope coefficient. The closer it is to 0, the more we are likely to conclude that there is actually no relationship between y and x. But what's interesting, though, is that it is still picking out, we've taken a slope of 3, but the random error, the epsilon, distorts this 3 to a 1.58. So let's say I had to take a much smaller standard error, 1. Well, now what happens? Now the slope is practically 3. It's very close to the true relationship. What do I mean by the true relationship? I just mean without the, strictly speaking, the true relationship has to have the, might depend on the definition, but I would think of it as the true relationship has to have the error term, although that's not necessarily the case. So look at this data. This data, it's centered, it's gravitating about y equals 2 plus 3x. You can even see the y-intercept if we include axes. These are your axes. And 2 is this point over here. So we can very quickly, we need a gradient of 3, right? So if I move 1 to the right, then I need to go up from 2. Do I need to go up to 5? So the gradient would be the true relationship passes from 0, 2, and then it needs to go through 1, 1, 1, 5, right? 1, 5. So the true relationship is this line over here. And we can now delete this, this, and this. So that's what we started with. We are using a predetermined true relationship. And now, of course, the whole point of this modeling is to actually determine that relationship. The observations aren't perfectly on the line due to the error term. Why do we introduce an error term? Well, think of it as perhaps the two major reasons are you aren't necessarily taking all the variables that influence the output into consideration. Certainly in this case, this is simple linear regression. You're only working, in fact, with one variable. There are very few things in the real world that only depend on a single variable. Just think of how you could change your current studying habits, techniques, diet, circle of friends, course material, lectures to impact a grade when it comes to studying for an exam. But over here, we're taking a single variable. You can't take much less than a single variable, can you? That's one reason why we need to allow for an error term. Another one would just be errors in measurement. If you ever had lab reports, very often in the very first page, you list the measurement errors. If you're using a ruler that can only measure up to the nearest millimeter, or half a millimeter perhaps, then your readings, your measurements, they're only accurate as far as your measuring tools allow for accuracy. So that those are usually the two most commonly cited effects that require us to take a epsilon term. Okay. So we've fit our model. We have fit our model, and we don't quite get an intercept of 2, but it's quite close to 2. And we don't quite get a slope of 3, but again, to one significant figure, it is certainly close enough. From where did we get these two values? These are the beta naught hat and the beta 1 hat. It is where are the formulae? It is these two formulae. Now what we could do is we could try calculating them ourselves. And notice that the slope, not the slope, the estimated intercept value depends on the beta 1 hat. How do you calculate beta 1 hat? You first need x bar and y bar. Now what are these? X bar is the mean of the x data. Y bar is the mean of the y data. So that's the very first thing we could do. We could talk about x bar, which is the mean of vector x. Y bar, this would be a single number for each one. So we have x bar and y bar. These are their values. These two over here. Then we need to create the vector. It's a vector, right? It's indexed on I. This vector of values, this set of n values, this set of n values, you're calculating the distance between each observation of x and the mean of x. We multiply and we sum. So let's have a look at this in R. Actually, really easy. You do x minus x bar. Actually, is it easy? Would that work? It probably has worked. So I guess what it does is that for every value in x, it subtracts x bar. For every value of y, we subtract y bar. And then we need their product. Then we need their product. And now we just sum. Now we just sum everything. And there you go. 364.1544. We need to divide it by the denominator. And the denominator is basically the same thing, but instead of multiplying this by the y, I minus y bar, it's this times itself. So that shouldn't be too difficult. It's just this times itself. And there we go. Let's look at this again. Oh no. Do we have the same? We don't have exactly the same. It might be just because it's rounding though, right? So 2.930, 2.9297. Now, if you're asking where do we get these formulae from, this is just the differentiation that we've been mentioning these past few sessions. You need to minimize the residual sum of squares. We could do this. Might be easier in Excel. I think in that case, just look at the Monday session, or it was maybe the session before that, where we worked in Excel. Okay. So taking a step back, we have the data. We're trying to fit a linear model. And we're estimating beta naught and beta 1. There is the true beta naught and beta 1. That's what we started with, 2 and 3. Our estimates are these two. Now, since they are estimates, that leads us to two questions very naturally. How good is the estimate? What kind of error is there associated with that estimate? And the second question is, how accurate is the model? So we have these two questions, which are addressed in, I think I skipped it. Here we go. Assessing the accuracy of the coefficient estimates. That's 3.12. And the next one, which is assessing the accuracy of the model. And this is probably quite an important section, which is why we're repeating a lot of it today. It's the first time that many of us are considering the error within a model's estimate. Okay. Now the idea is the following. And it starts off, the book motivates all this by taking us back to secondary school data handling, where you're only looking at data values with just one piece of information, just y. We're not relating y to anything. And we have this distinction between the population mean and the sample mean. Let me tell you what we have in mind over here. Just before we continue. Let's take, for example, a normal distribution. Let's take a normal distribution. Normal distribution is a bell curve. We've often said it's the distribution that occurs quite a bit in nature, especially when there's like genetic variation. So think of heights of I don't know, 30-year-old men, for instance. Now, let's say that we collect 100 observations, and these are going to be our y's, but our sample y's, sample y data. We go out, we measure people, we measure 100 of them, and we're going to play God. We know the mean, it's 180, and we know the standard deviation. Now, in reality, you wouldn't actually know these. This is the population mean, This is usually what you want to infer from a limited sample. You want to get to the population mean. And we'll take a standard deviation of, and again, I'm just inventing these numbers, but you can think of this as being measured in centimeters. Is there a way I can round to 2 decimal places? If I write around, it's just easier to have the data this way. Okay, so these are our 100 observations. We can do a histogram, which is a great way of summarizing data usually. And that's our histogram. It's a bell curve. Now, since I only took 100, it doesn't look like much of a bell curve. And that's the whole point. The point is that the smaller your sample, the less insight you get into the real shape of the data. If I took 10,000, now we're expecting a bell-shaped histogram. Now look at that. Beautiful, isn't it? This is what I mean each time by a bell curve. And notice the normal distribution has this really nice property that that the mean of 180 coincides or should coincide with the mode, so with the most frequently occurring data value, and with the median. So half your data values are above, or they have a value above 180, the other half have their value less than 180. But we're going to take just these 100. Okay, and that's your sample Y data. Now the next thing you would do is calculate the mean. You want to get an idea of the mean. So sample Y data, and it's 178.03. So that's the first calculation. That's the first summary. And we're going to call this the sample mean, right? We're going to call this the sample mean. It's not the population mean, or we don't know if it's a population mean. It's going to be probably quite close to the population mean, or at least that's what we would hope for. But now we need to place it in the context of an interval. If my sample mean is 178.0314, by how much? What are the extremes? I have likely underestimate. If I'm underestimating, and in fact we're underestimating, right? The true mean is 180. If I am likely underestimating, to what extent might I have underestimated? And if I'm overestimating, to what extent have we overestimated? Now, this is where the standard deviation comes into play. There is this formula, and we'll read it. Although before reading it, I think it's worth going over this paragraph over here. If we could average a huge number of estimates, do we get that? If we could average a huge number of estimates of mu, so right now we only have one estimate in R, obtained from a huge number of sets of observations, then this average would exactly equal mu. Let's just... Now, is there an easy way of doing this? I'd like to create, and I've never done this before. I'd like to create for example, 50 of these data sets of 100 observations. Now, whenever you need repetition, that's the 4. So what if I said k data sets from 1 to 50? But how would we do this? How would we give each... Maybe there's another way of doing that. Or else, you know what? Why don't I create 5,000? Why don't I create 5,000? And then only take... I think I wanted 500, right? Not 5,000. And then only take the first 100, then... No, it was 5,000, right? 5,000. Because I'm saying we'd have 50 data sets, and there are 100 observations in each data set. I'm not entirely sure I'm going to manage to do this. Because what I want is that I create 50 data sets. I don't know how to do it, though. I don't know how to do it. What I wanted to show you, and I might need to do it manually, is that each data set gives you a specific mean. How would I create... No, I think we can do it. So let's not give up so easily. Let's do it like this. So I've created 5,000 observations, but I'm going to say the first 100 or one observation. And then we need to calculate the mean. So what if I said mean? Let's do it like this. Let's do it like this. If I wanted only the first 100, wouldn't I say, what's the notation? What's the syntax? This is the syntax, right? And if I wanted the last 100, wouldn't I say 4901 up to 5,000? Like this. That's the last 100, correct? That's the last 100. So is there a way of creating a formula? Is there a way of creating a formula that first considers only the first 100, and then it considers the next 100, and it keeps on doing this 50 times until you get to from the 4,901st to the 5,000, up to the 5,000. It shouldn't be too difficult, right? Let's start with this formula. This is very easy. These are just arithmetic progressions, aren't they? So what I would say is sample y data. Surely it's very easy. I just have a common difference of 100 each time. So which formula do we learn? A plus n minus 1 times d. 1 plus k minus 1 times 100. So that should give me 1, 101, 4901, up to 100k. Up to 100k. Let's see if this works. Let's see if this works. A really useful thing is to just take an example. So for example, if k was the 30th data set, if k was the 30th data set, no, that hasn't worked, has it? We've got a lot of NAs. So let's see. What does this evaluate to? If that evaluates to 901, that looks fine. This evaluates to 3,000, that looks fine. I think it's just the way maybe I've typed it over here. Maybe I need brackets as well. Oh, great. See, you're in a way you're kind of debugging your code. You're taking a specific one and you're seeing, does it work? Well, I would really know if it works if I had to compare. It looks like it's worked, but to better compare, what if I do 2901? 2901. Yeah, see, look, 184.69, 184.69. What if I said 3,000, 3,000? Again, 178.82, 178.82. So we can delete all this. Of course, we need to reflect the changes made here. But now we're going to calculate the mean of each data set. The mean of each data set. The mean of each data set. And we're going to save it somewhere. So I'll call them mu hat. Mu hat is, let's use the book's terminology. Estimates of mu. Estimates of u. A huge number of estimates of u. Let's call it that. Let's call it that. Huge number of estimates of mu. We just saved the null vector for the time being. And then we're going to say, call this, for example, mu hat or mu hat k. Mu hat when I have k for the kth data set. And then just take this, and for each data set, include it in this vector, like this. So what is it going to do? We have 5,000 data points, but think of them as 5,000 data points, 100 from each data set. So imagine all of us, but it is 50 of us. We all go out in the real world, and we each take 100 measurements. We observe 100 data subjects, and we said heights of individuals. So there is my data set, there's your data set, her data set, his data set. But so far we've saved them all in a single sort of, think of, we've all saved our observations in the same file. Now what this is doing is it's looking at the data in blocks of 100 observations. The first 100 from surveyor number 1, the second 100 from surveyor number 2. And we're going to calculate the mean for each of these 50 data sets. Now, each time you're going to expect a number which is close, whatever we mean by that, to 180. Let's do it. Object Z not found. Yeah, because I called it Z, but I should have called it mu hat K. Sorry about that. I usually take Z in these loops. Okay, and now it's worked. And here it is. This is the mean for each data set. Now, would you like to look at the summary of these estimates of mu? So look at the variability within our estimates. It's between 177.6 and 182.2. And isn't this just amazing? The mean, at least 1 dp, is precisely 180.0, which we know, because we set it up that way, is the true mean. Now, would you know the true mean in practice? No, of course not. That's the whole point of doing an exercise like this. But we have the true mean this way. Now, can you calculate this 177.6 and this 182.2? Yes, by using this formula. This is going to give you both sides of the interval. It's centered at 180. It's centered at the true mean. And this is called the standard error of mu hat. Mu hat is what you're estimating. And the definition is the following. It is sigma squared, where sigma squared is the standard deviation of each of the realizations yi. But there is a footnote. Let's see. Yep, that's okay. We don't need to go into that. Division by the number of observations. Let's see. So the standard deviation of y. Do I do it only for one? You would only have one data set though, right? In real life. You'd only have one data set. So let's take this data set. Let's take this data set. And let's say data 1, the first 100. We should stop doing that. There is the mean of data 1. There is the standard deviation of data 1. That's the square root of the variance. There's probably an easier way of doing it, but square root of the variance. And that's 10.03. As you would expect, the true standard deviation is 10. And now, to calculate the standard error in your estimate of mu, so important, this is so important. Your estimate won't be precise. You won't know if it's precise in any case. So you divide the standard error squared, which is just the variance, by the number of observations, so by 100. So this means that you've created an interval. You take your mean, which is just the estimate, and you add this, and this is, I guess, must be some kind of confidence interval. What do I mean? So for example, for beta 1 hat, you get a 95% confidence interval by multiplying the standard error by 2, and then adding and subtracting from your estimate. Probably need to do something over here as well. You can only create these confidence intervals if you say, okay, with 95% certainty or with 80% certainty, how wide is the confidence interval? But it depends on the level of certainty that you would like. Although having said that, that's very often arbitrary. We say 95%, we say 99.5. It's not like we're calculating these figures. We start from them at the outset. So that was secondary school level. When you have a sample data set, if you simply calculate the mean, that is an unbiased estimator. What do we mean by an unbiased estimator? If we had to collect sufficiently many data sets, calculate the mean of each one, and then calculate the mean of those means, then you would expect that would be exactly equal to the true population mean. This is what we mean by unbiased. What we mean is these means, where we're trying to determine the true mean, they are, as much as some of them overestimate the true mean, there are others that underestimate the mean. So some of them were, so the highest one was 182.2. but the minimum is basically canceling that maximum. And we could sort this data. This is something is very simple. It's very simple, but I'll do it so it's something else that we can say we've done in R. This is basically going to make up for this. They're now in ascending order. This one is going to be basically make up for this one, etc., etc. Now we're going to do something similar with beta 1 hat and beta naught hat. To calculate their standard error, we use these. They look quite intimidating, but they're not that difficult. These two formulae. Now the thing is, would you have sigma? Because the x's that's your raw data, and the n is just the number of data points. Would you have sigma? No. You in practice you wouldn't know sigma. Why? Sigma is a bit different to the sigma over here. This sigma is just the variability in your raw data, where you're only looking at y's, y1 up to yn. In linear regression, the sigma is the variance of the error term. And you wouldn't know the error term in practice. In practice, you would not know the error term. Let's go back to what we were doing over here. If we plot all this, if this is your data, and it's a scatter plot, it's y against x. You don't know your error term. We know it, but this is quite an artificial example. We're doing it exactly the other way around to what you would have in practice. We know the error term. It's a normally distributed random variable with zero mean and a standard deviation of 1. By the way, when it's these two parameters, you refer to it as the standard normal. It's standardized as a standard normal random variable. But if you're just looking at this data, you don't really know you could pass a line through it and maybe get an idea. You could get an idea, perhaps. You could say, of course, it depends on how good this line is. So there's a bit of circular logic over here, because to pass that line might be some circular logic over there. So instead, since we don't know the error term, we define this over here. This is known as the residual standard error. It is the RSS divided by n minus 2. And we could try doing that right now. Where's our data? Our data, let's call it data xy. So this is our data. This is our data. How do you calculate the residual standard error? First of all, you need RSS. Okay. Now, how do you get RSS? RSS is a single value, and it depends on the residuals. Now, how do you get those residuals? The residuals depend on the difference between the prediction and the, let's take maybe a more interesting one. Let's take standard deviation of 5. So let's look at this is our data. This is our data. we have this. And we can delete all this. Now, for this specific data set, we have 2.067 and 3.12 as our parameters. Now, we probably don't actually have enough time to calculate the... I wonder if there's a formula somewhere. It would be nice if maybe... If I save this as linear fit, everything's an object in R. So when you fit a linear model, you could even... Does it give us the RSS? Look. You see, there are the residuals. Degrees of freedom. See, this is like n minus 2, the 98. I don't know if that's a coincidence. But anyway, we seem to have our residuals over here. So how do you get them? How do you get them? Can I type linear fit? Yeah, these are all your residuals. So you can actually square them. You can square them because it's the residual sum of squares, right? You can square them and take their summation. And I wonder if that appears somewhere. 96.53. Was it somewhere over here? 96.53. Okay, so apparently we have to work it out ourselves. It's not in this summary, something like these diagnostics. To calculate, to approximate the sigma squared, we calculate the square root of RSS divided by n minus 2. So there's RSS. Remember, it's what the linear fit, and we're going to conclude. Final 2 minutes. It's what the linear fit is trying to minimize. So when we have this fit, when we have these 2.067 and 3.120, these two parameters minimize the residual sum of squares. So you can, for this specific data set, you cannot get less than 96.53025. Now, to calculate an estimate of sigma squared, we take the square root of the RSS divided by 100 minus 2. And look, that's 0.99. Ours was 5. I wonder... That's odd. That's odd. Shouldn't they have been close? Shouldn't sigma squared... Sigma squared can be estimated from the data. Strictly speaking, sigma squared is the variance of epsilon. Let's run everything again. Okay, very good, very good. So clearly I must have maybe I probably when we did it the first time we had one of the variables I hadn't updated it. So look, you don't know in real life you don't know that your error term has a standard deviation of 5. You wouldn't know, right? But if you use this formula, square root of the residual sum of squares divided by n minus 2, you should get something that approximates, something that estimates. So I'm thinking this is sigma. This approximates not sigma squared. In fact, that would explain the square root. This approximates not sigma squared. It's not entirely clear. It approximates the residual standard error. So the residual standard error approximates sigma. So strictly speaking, you should have a hat because this is an estimate. This is an estimate. You don't know it. So strictly speaking, this is an estimate. Same thing over here. This is an estimate. You don't know the true standard deviation of your error terms. And this is an estimate as a result. Now with these two, and we'll conclude on this point, with these two, and we'll go into this in more detail. What we'll likely do is these next few sessions will just be revision of the Monday session and the Tuesday session, because these are some new concepts which it takes some time. It takes some time to appreciate what they're doing and how they're interacting with the rest of the material. But with these estimates, the standard error of beta 1 hat and the standard error of beta naught hat, you get an idea of the error within beta 1 hat and the error between beta naught hat, which is very important for this hypothesis testing. If the error is very large, then you might have specific values within that interval, because you might have 0 within that interval. And if it's the interval for the beta 1 hat, then you might actually have to conclude, okay, we cannot rule out that there's in fact no relationship between y and x. But we'll stop here for tonight.